will tell us about the section conjecture. And we ask people to not only write in the chat, but mainly try to raise hand using this button or speak up if they
Can everyone see me and see what I'm sharing on the screen?
Yeah, I can see it.
Okay, great. All right. Well, it's great to be here virtually in Madison. Thank you so much for the invitation. And I wish I could be there in person. Hopefully I can come to Madison at some point in person soon, but this will have to do for now. So before I begin, I do want to reiterate what Mark just said, because I think there may have been a little bit of an audio glitch. So please do ask a lot of questions. I know the Madison seminar is usually like pretty interactive. And so if you want to ask a question, I suggest doing that in one of two ways. So first of all, if you look at the list of participants, you'll see there's a raise hand button. And if you click raise hand, I'll see that little symbol by your name and I can call on you, and then you can unmute yourself and talk. So I think I won't be looking at chat. So typing questions into chat might not help too much. And okay, I see Jordan though is saying the audio is a little bad. Can people sort of hear what I'm saying? All right, so we'll see what happens. Great. If you do want to ask a question about something that you think I might move on from quickly, I do think you should feel free to just like unmute yourself and ask me. Like, I don't mind at all. Okay, so with that, let me begin. So I want to start by mentioning that everything I'm going to talk about today is joint work with Wanlin Lee, who spoke at Agonize yesterday, Nick Salter, and Padma Srinivasan, who also spoke at Agonize yesterday. So if I forget to mention their names next to something, that's my fault. They are, co-authors on everything I'm going to talk about here. Okay, so I want to tell you a little bit about some examples of curves for which the section conjecture is true, and a sort of fun new way of constructing such examples. Before I do that, I should probably tell you what the section conjecture is. So let me start by doing that. So what's the situation? So we start with X, which is a smooth, proper, geometrically connected curve over some kind of arithmetically interesting field. So for me, by an arithmetically interesting field, I mean maybe a number field or a p-adic field, or maybe a finitely generated extension of one of those. And you can make other statements over other kinds of fields, but for the vast majority of the talk, that's the situation I'll be in. So in particular, number fields and p-adic fields both have characteristic 0, and that will simplify a few things I say. Okay, so like, suppose you're given a curve k, maybe over q, so like a curve defined by polynomials with rational coefficients. So maybe the first question you might ask yourself, if you're a number theorist, is to find all the rational points of that curve. So that's like a famously hard question. And you can ask even maybe an easier question. So you can ask, like, is the set of rational points empty? Okay, and these questions are famously hard. If X was like an arbitrary variety, and if you replaced like a number field with Z, it's known that it's not decidable whether or not an arbitrary variety has any Z rational points, or arbitrary Z scheme. I think that's the analogous question over Q, for example, is not really known. I think it's expected that it's undecidable whether a variety over Q has a rational point or not. I think it's expected that it is decidable for curves, and that would follow from the ABC conjecture, for example, or like an effective version of the ABC conjecture, or I think from the section conjecture. Okay, so what's the section conjecture? Well, it's some kind of like conjectural answer to these questions. So it's some recipe for listing all the rational points of a smooth proper curve of genus at least 2 over, say, a number field in terms of some kind of geometric data. So in terms of the fundamental group of your variety. So let me say what I mean by that. So suppose I have for now a curve, but any variety, and I take a geometric point. So here this X bar is a geometric point. It's a K bar point of my variety. So to that data, I can associate in a functorial way a profinite group called the etale fundamental group. And so that's denoted pi1 etale of X with the base point X bar. Just like in topology, you need a base point to define a fundamental group. And that's defined in terms of the following equivalence of categories. So a finite set with a continuous action of pi1 etale is supposed to be the same as a finite etale cover of X. Okay, and what do I mean by the same? I mean that both of these things form categories, and that there's going to be a canonical equivalence of categories between these two sets, between these two categories. And I can write down what it is explicitly. So given a finite etale cover of X, Y, you send it to the fiber over our geometric point X bar, and that's a finite set. And in fact, I mean, this defines a functor to sets, and if you'd like, you can define pi1 to be the automorphism group of that functor. So I've told you an actual rigorous definition of this etale fundamental group. So are there any questions about the definition? So far, it just seems like some categorical nonsense. Let me just kind of justify it to you a little bit while you decide whether or not you want to ask a question. So what this is trying to encapsulate is the theory of covering spaces. So the theory of covering spaces in depth transformations. The right-hand side over here, these finite etale covers are supposed to be covering spaces of X. And here, this is the fiber of a covering space. And what is this saying? It's saying pi1 is the natural thing that acts on fibers of covering maps. Okay, so this is a good definition. If you'd like to know more, you can read SGA1, which is where Grothendieck worked out most of the basic properties of this group. Okay, so let's talk about it. So typically this group is kind of mysterious. So let's try to analyze its structure a little bit. So suppose I'm given X, which is still going to be let's say a smooth projective curve over a field K, and X bar is a geometric point of X. So I said X is a curve over K, so it maps to spec K. And well, X bar also maps to spec K. So we have kind of a silly map of pointed varieties, right? From X bar to spec K X bar. So I told you that pi1 was functorial up here. So what that means is that I get a map from the etale fundamental group of X to the etale fundamental group of spec K. So let's figure out first, what is the etale fundamental group of spec K? So what is a group which classifies finite etale covers of K, aka separable field extensions? So if anyone wants to type it into chat or unmute themselves and answer, that would be great. So my hint is that it's related to the fundamental theorem of Galois theory. All right, so someone has written the Galois group, and that's right. So it's the absolute Galois group of K, so the Galois group of K bar over K. And I want to point out some subtlety here, which is to define an absolute Galois group, you need a choice of algebraic closure. And maybe at first glance, it's not so obvious where that's coming from on the left. Well, where it's coming from is this map from X bar to spec K. So remember, X bar was a geometric point of X, a K bar point. So we get a map from spec K bar to spec K. So that's a choice of algebraic closure. All right. And what's the kernel of this map? Well, it turns out it's the etale fundamental group of X base changed to K bar, again with this base point X bar. All right, so maybe you feel like that doesn't tell you that much. So we have a surjective map from the etale fundamental group to the absolute Galois group of K. That's maybe a pretty mysterious thing itself if K is like Q, but if K is QP, maybe it's better understood. And then the kernel is this thing which is the etale fundamental group of X base changed to K bar. So before I say a little bit more about what this is, let me just remark, like, maybe this should be familiar. So like in what kind of situation do you have an exact sequence of homotopy groups? It's when you have a fibration. So what you're supposed to think is that XK bar is the fiber of the map from X to spec K. And well, that's true, it's the geometric fiber of that map. All right, so what is pi1 etale of XK bar? Well, X was a curve, remember? So I claim this is something pretty concrete. So it turns out, since I'm over a field of characteristic 0, that this is basically what you would expect. So if you had a curve over the complex numbers, its fundamental group would be generated by 2G things, A1, B1 through AG, BG, subject to one relation, namely the product of the commutators equals 1. Okay, and so this can't quite be right because I told you the left-hand side was a profinite group, but it's the closest thing it could be. It's the profinite completion. So this here, this hat means profinite completion. Okay, so what that tells us is that this etale fundamental group of X is an extension of something arithmetic, namely the Galois group of your ground field, by something geometric, namely something we kind of well understand, namely the something that's closely related to the usual topological fundamental group of an algebraic variety over C. Okay, and nonetheless, like this group is really mysterious, and what's the most mysterious about it is kind of this extension data. Okay, so Grothendieck's conjecture, the Session conjecture, is going to be somehow about that extension data. So let me introduce a little bit more geometry of this group, and then I'm going to state the conjecture. All right, so suppose we have a rational point of X. So X maps to spec K. What's a rational point? It's like a section to that map, right? It's a map from spec K to X. And again, pi1 is functorial. So if you have a section to the map X to spec K, you should get a section to the map from pi1 of X to pi1 of spec K. So that's called a pi1 section. Okay, and I put a star here because there's a little bit of subtlety. So does anyone see what the subtlety is? I know some people in the audience do, because, for example, there's at least one person in the audience who knows a lot more about the Session conjecture than I do. But I'm sorry, Mark?
Outer automorphisms?
Yeah, so the geometric way of saying what I think you're saying is that the section is not necessarily a map of pointed varieties, right? Because we had some base point of X, which I conveniently left out of the notation. And then if spec K goes to some other point in X, you don't get a map of pointed varieties. And pi1 was only functorial for pointed varieties. So, okay, well, you could just move your base point to like where your section hits, and then you'd have a map of pointed varieties. So here, well, moving your base point kind of changes things up by inner automorphisms, just like in topology. So what you really get is only one of these pi1 sections well-defined up to conjugacy. All right. Nonetheless, we do get a map to pi1 sections well-defined up to conjugacy, and so that's the upshot. We get this map sec stands for section, from rational points of X to pi1 sections up to conjugacy. And just a reminder, a pi1 section was a section to this map of groups, so a continuous map of groups, so that going up and going down is the identity. All right, are there any questions about that? Great. All right, so what is Grothendieck's conjecture? So X is a curve of genus of at least 2 over one of these arithmetically interesting fields, so like a number field or a p-adic field. So then the conjecture is that sec is a bijection. So in other words, you can, for example, decide if X has any rational points by checking if it has any pi1 sections. You can count the rational points by counting the pi1 sections up to conjugacy. So this is supposed to be a purely group theoretic recipe for understanding all the rational points of X. All right, are there any questions about that? Let me just remark that like the finite quotients of the etale fundamental group are like in principle computable things, although not very quickly computable. So this is actually in some sense an effective recipe. I'm not going to discuss in detail like the exact sense in which it's effective, but at least some questions about rational points of X become decidable if you believe this conjecture via computations about the etale fundamental group. All right, so let me say a little bit about why you might believe this conjecture. It's not so clear to me like why Grothendieck believed it. I think at the time there wasn't really a lot of evidence for it, and in particular, I think like when he made the conjecture, which I think was in the 80s, there were probably no examples of curves for which it's known. So I want to give you a list of at least some examples of cases of the Session conjecture that are known. So examples of curves for which the Session conjecture is known. And I'm not going to give you an exhaustive list, but I want to at least give a few examples. So first of all, Jakob Stix, who's in the audience, has given, well, a few examples of curves to which the section conjecture can be checked. Well, so as far as I know, the first example of at least a curve in the literature for which the section conjecture was checked was in 2008, and it was a so-called trivial example. And I don't mean trivial in the sense of like mathematically trivial. It's actually a really cool paper. So I mean trivial in the following more precise sense. So he was making examples of curves over p-adic fields where this map, sec, is a bijection. Well, what's the easiest way to show that a map of two sets is a bijection? Well, it's if this set of pi1 sections is the empty set, right? Any map to the empty set is a bijection. So that's a fun fact from set theory. So what does trivial mean? So trivial here means that the set of pi1 sections is the empty set. So if you can construct a curve where the set of pi1 sections is the empty set, you've constructed a curve for which the section conjecture is true. All right. So then shortly thereafter, Harari and Szamuely made a very beautiful example of a trivial example over number fields. Okay, so that wasn't the main accomplishment of their paper. If you have an example over p-adic fields, it's very easy to turn it into an example over number fields by approximating it. But the cool thing about the Harari-Szamuely example is that it has everywhere, it has points everywhere locally, but not globally. So it doesn't come from any p-adic example because at every decomposition group there is a pi1 section because there's a rational point. So this is also a counterexample to the Hasse principle. And there are a lot of other examples along these lines, including some non-trivial examples. Salmi, what's looks like you have a question? You can unmute yourself to ask it. Oh,
yeah. So you can finish your sentence before I ask. I was going to ask a question about the conjecture itself. So.
Oh no, go ahead.
It was about. So why do you need the genus to be bigger than or equal to 2? Like, is the infiniteness of rational points a problem?
Yeah, so that's a good question. So in genus 0, you can, it's not so hard to see that the geometric fundamental group is trivial. So the etale fundamental group is just the same as the Galois group. So there's only one section up to conjugacy, namely the identity. But rational curves typically have infinitely many points, as you said. And then in the case of elliptic curves or genus 1 curves, you can just directly compute that the set of sections is too big. So it's just false for lower genus. One remark is that if the genus at least one is at least 1, then sec is always injective. And that's true for abelian varieties in general. All right, I think Asvin and David both are raising their hands. So Asvin, do you want to go first?
Does the section conjecture for number fields imply it for p-adic fields, which are completions of the number field?
Not as far as I know, but there are a couple experts in the audience. So if someone knows differently, then I'd love to hear it. All right, it looks like no. Oh, go on.
For evidence 1, Stix's theorem, are there examples where you can verify that there are no pi1 sections without using this theorem?
So I'm going to talk about a bunch of examples, but I mean, so for example, Harari-Szamuely's example is another way of verifying there are no pi1 sections. So it's when I write trivial, I mean that there are no pi1 sections.
Great.
Yeah. All right. Are there any other questions before I discuss the last kind of class of examples that I want to talk about today? All right, and by the way, Asvin and David, you're still raising your hands. So if you have another question, that's fine, but I want to, yeah, great. All right, so there's one more class of examples I want to talk about today, and those are due to Hain in 2010. And those are kind of geometric examples. Okay, and what examples are there? It's you take the kind of generic curve over the function field of mgn. And here I think this doesn't work for arbitrary fields. So for example, I think you can take k to be a number field. So okay, so this is pretty interesting, I think. So it doesn't quite fit into the situation we gave at the beginning because the function field of mg is not a number field or a function field, but it's a finitely generated field. That's fine. I think we believe the Sexton conjecture in that case. So the other cool thing is that if n is not equal to 0, this is kind of not a trivial example. And that's because the universal curve over the generic point of mgn has rational points, namely like the n points that come from the definition of mgn. So here, mgn is the moduli space of genus G n-pointed curves. So any curve over a point of mgn has at least n points. Okay, are there any questions about those examples? So this was really not exhaustive. So I think Jakob Stix, who's in the audience, has also given examples of curves over number fields where they satisfy the Session conjecture in kind of a non-trivial way. And then there are other examples in the literature too. All right, so what I want to talk about today is a sort of machine for making many new arithmetic and geometric examples, so geometric like in the sense of Hayne. And they're going to have a couple cool features. So first of all, I'll say what I mean by many. But the technique, I think, is cool itself. So it's going to use an analysis of the degeneration of certain Torsion cohomology classes and the cohomology of MG with some local systems on the boundary of MG. So this will give a kind of cheap construction, and it'll be closely related to some of Stix's examples. And then it'll also give a kind of very cheap version of a strengthening of Haynes' results in the case n equals 0, so the kind of trivial case. So Arnav, it looks like you have a question.
Yeah, hey.
Hey, Arnav.
I don't know exactly what all the examples are and how they were constructed, of course, but you know, if they came from some like modular construction, I might have more intuition as to them. Do you know if the Session conjecture says something particularly interesting, or if there's an approach to it for like modular curves, for example?
For modular curves. That is an interesting question. So I think, yeah, so I've thought about this a little bit. I think, so you might ask like, okay, like maybe we can figure out something about how Galois acts on pi1 of modular curves, at least as like a first question. Sure. And there's like a obvious thing to try, which is like the pi1 of a modular curve acts on the Tate module of the universal elliptic curve, right? And we also know how Galois acts on that thing. So the problem is that representation only captures a really tiny portion of pi1 of a modular curve. And that's because of the failure of the congruent subgroup problem. So like analytically, the map from pi1 of a modular curve to GL of the Tate module is injective, right? So you'd think it would capture everything. But when you take profinite completions, it has an incredibly huge kernel. So somehow that representation doesn't tell you that much.
So can you do like Minhyung stuff, or I don't know who this is, like Degenerating or someone like, you know, take more of the unipotent.
Yeah, so Haynes' thing in this 2010 paper does use some of this pro-unipotent completion stuff. And I think obviously like Minhyung would love to prove the Session conjecture using his stuff, but as far as I know, there's not really a lot of progress in doing that. Jordan? Or Arnav, I don't want to stop you from talking.
No, that's cool. Yeah, thanks.
Yeah. So Jordan, you're raising your hand. What's up? I think you haven't unmuted yourself.
Oh, okay. Now I'm talking.
Yeah, great.
Yeah, so I would, in response to Arnav's question, I mean, for questions about how you can use the action on the fundamental group to get at something about points on modular curves, I would look to this work of like Jen Balakrishnan and Nitin Dogra and that group of people on one particular modular curve, X split of 13. And I would say that in a sense is a section theoretic approach in that it's seeing, as you say, the action of Galois on the quotient of the fundamental group by its third piece of its lower central series. And in some sense, they are ruling out sections by their method, although it goes a little bit deeper than that. Okay, I'm muting again.
Awesome.
Yeah, and I do think also like maybe Dogra has recently released something which works on quite like many modular curves, but it's not clear to me exactly how it's related to the section conjecture itself, rather than just finding rational points. Like I don't think they've, even though they've found all the rational points, like I don't think they've proven the section conjecture for those curves, at least as far as I know. All right, so the goal today is to produce a lot of examples, and I'll say here I have this word many, and I'll say what I mean by that. And then I'm also going to describe how to use kind of the same method, or as a corollary of the method, how to get some new kind of geometric examples. All right, so let me tell you a little bit about the strategy, and some like interesting things will show up in the strategy too. So what's the strategy? So first of all, I want to find some way of like obstructing a section. I'm going to try to produce some so-called trivial examples to the session conjecture. So I want to produce some curves with no pi1 sections. So how am I going to do that? I'm going to try to find some cohomology class in the cohomology of MG, and I'll actually give you a couple examples of such things. So that if I have a point of MG, so a point of MG is a curve, so I'm going to call it C, namely, I'm thinking of the point as an actual curve. Well, then I can, if I have a cohomology class on MG and a point of MG, then I can pull that class back to Galois cohomology. Okay, and what I want these classes to have is the following property. I want that if you pull them back to Galois cohomology of our point, if they're non-zero, then I want my curve to have no pi1 sections. Okay, so I'm going to produce a couple examples of classes in the cohomology of MG. Here I mean etale cohomology of MG over Q with coefficients in some local system, which have that property. So namely that if I pull them back to a point of MG, they obstruct pi1 sections if they're non-zero. Okay, so once you do that, then you win if you can prove that there are a lot of C, a lot of curves, so a lot of points of MG, so that when you pull these classes back, you get something non-zero. And why is that? Well, it's because the classes obstruct pi1 sections, and we're trying to produce curves with no pi1 sections. Okay, are there any questions about that that strategy? So Jordan, you're still raising your hand, but I think probably you don't have a question right now, but maybe you do. So if you do, you should feel free to unmute yourself. Oh, okay. Great. So I just want to remark, I mean, so suppose I have like a cohomology class on a variety with coefficients in some local system. You could ask, like, is 2 always true? Like, can you always specialize it to infinitely many points, maybe like closed points or something, so that it's non-zero? And the answer is just no. So this 2 is not formal. It's something you have to prove in a way that like depends on your actual cohomology class. And I'm not going to give a detailed example, but like, for example, it's not so hard to construct certain Brouwer classes on non-split conics so that they restrict to the 0 class at every closed point of the conic. So 2 actually requires a little bit of work. Okay, so let me say a little bit before I describe these obstruction classes OI. I want to tell you like what we're going to need. So like how we're going to show that they're going to specialize in a non-zero way to a lot of different points. So here's the schema. So suppose I have some like class in H2 of like a variety, or maybe MG, with coefficients on some local system. So I just told you like it's not formal to show that it specializes to a non-zero thing in lots of different ways, even though that's what we want. So here's the thought. So what if what if O was in H1? I mean, it's not, okay, but we're going to try to get it there. So if O is in H1, it's actually not so hard to see by a little Cherepanov argument that there are lots of specializations, or lots of non-zero specializations. So I'm not going to give the detailed argument, but this is like analogous to some version of Hilbert irreducibility, or like the statement that if you have a Galois cover of geometrically connected varieties and a point downstairs, you can usually lift it to a point upstairs where the extension has the same Galois. It's exactly the kind of thing, the same kind of thing. All right, so what we want is we want to get something in an H1, and what we have is we have something in H2. And so I know of like one good way of getting from H2 to H1, and that's to use Geison maps. So that's what we're going to try to do. So let me give you a brief intro to Geison maps. So suppose you have a variety Y. So here I've drawn a picture of Y and a divisor D inside it. And here I'm going to let U be the complement of D and Y. So here's the notation, and here's the picture. So U is the complement of D and Y. So then I claim there's a Geison map, which goes from the cohomology of U with coefficients in whatever local system you want. So starting in H2, and it lands in H1 of D with coefficients in something else. So what is that other thing? So I've written it as L sub I, and let me say what I mean by that. Well, if you have a smooth divisor inside of some smooth ambient thing, then there's a well-defined conjugacy class in pi1 of the complement, which is given by taking a loop around your divisor. So that's that pink loop here. And since L sub I is the co-invariance of L under I. So there are a couple of different ways to think about this. So if you're analytically inclined, you can think of this map as like integrating along fibers of the map from the kind of circle bundle and the normal bundle around D to D. So you're like integrating along a circle, and that's why you're taking co-invariance along that circle. If you're more algebraically inclined, the way I like to think about it is this. So you start with cohomology on U, you restrict to a punctured neighborhood of D inside of its normal bundle. So that's like some circle bundle around D. And then you look at a differential in the Leray spectral sequence for the map from this circle bundle to D. Okay, so whatever that is, it's some algebraic gadget that goes from H2 of U to H1 of D. So suppose we can find some D where this Geison image of our class that we're interested in is non-zero. So then we get something in an H1, right? So then by Chebotarev, there are going to be lots of points, there are going to be lots of points on D here, so that when you pull them back, you get something non-zero. So, okay, so I've taken my class, I've moved it to the boundary of my space, so I've kind of degenerated it and gotten something in an H1. And then by this more or less formal argument above, I found lots of points where it specializes to something non-zero. So I don't win yet though, right? Like I want to find points where my like original class specializes to something non-zero, not my new class. Okay, so what do I do? So I'm gonna choose, so an FQ point of D, let's call it X, where my class restricts to something non-zero. So here I'm gonna take H1 of FQ, and I have, here I have O, here I have the Geison image of O, and here I have X star of the Geison image. And I want that to be non-zero. Okay, so that's something I can do. That's a little application of Chebotarev density. But I want my original thing to be non-zero. So what do? I'm just going to lift this point to a QP point of U. So here, let me call that X tilde. And that I can do because Y is smooth. For example, MG bar is smooth in the actual application. So now I get a commutative diagram like this. So O maps to the pullback of O along X tilde. And we know that the Geison image of that is 0. So here I'm omitting the fact that the Geison images make sense in mixed characteristic and that sort of thing. And so in particular, the geometric description I gave doesn't work in that case, but it's fine. Okay, so what do I have? I have that if I go along this bottom left thing, I get something non-zero. So that means the image under this top map must be non-zero. Or that means my original thing must be non-zero. So that means I've produced a lot of QP points, for example, of U, so that my thing is non-zero. So I've produced a lot of non-zero specializations. Okay, so that was a little complicated. So let me just recapitulate the strategy. So what have I said? So originally I said we had some obstruction classes here, these OI, these obstructed pi1 sections. And we wanted to show that there were lots of points in MG so that they specialize to something non-zero at those points. And so what I've just explained using this Chebotarev argument is that it suffices to find a divisor D in the boundary of MG so that the Geison image of my class in that boundary locus is non-zero. All right, so are there any questions about that strategy? So for the rest of the talk, I'm going to explain how to understand these OIs, like how to find some obstruction classes like this, and then how to find like places in the boundary where they Geison to something non-zero. And let me just remark at least that some of the time, none of the usual like codimension 1 strata and MG bar will actually work. So we're going to have to modify the compactification of MG we're using. Okay, and I'll explain the solution later, but let me just remark it now. So the solution will be to blow up certain boundary strata in MG bar. Okay. And let me just remark, I can now say what I mean by many earlier. So I told you I was going to produce many kind of new examples where the section conjecture is true. And so what do I mean by many? So I mean many in the sense of the quantitative estimates from the Chebotarev density theorem. And let me just remark, I mean, like the restrictions of the classes I write down to Galois homology are going to be like pretty computable in practice. So what this means is that in principle, you can use this not just to prove that many examples exist, but to actually write down real examples with like equations. All right. So before I move on, the plan for the rest of the talk is I'm going to introduce these classes OI and then kind of explain why they have non-zero Geison image and then draw some consequences from that. Before I do that, are there any questions? All right, so now let me explain how to do this part one. So how to find some classes in the cohomology of MG which obstruct pi1 sections. I'm going to call these arithmetic Morita classes. So what are they? Well, they're going to be the sort of natural things you would write down. So here, let's look at MG. So that's the moduli space of genus G curves. Because it's the moduli space, it has a universal curve over it. So the fiber over a point in MG, well, a point in MG is just a curve, and the fiber over that point is that curve. So let's say I take a geometric point of this upstairs thing, the universal curve. That maps to some point of MG, so it maps to the curve that point lies in. Well, you're supposed to think this is a fibration, so you get a fiber sequence for etale fundamental groups. So you get a sequence which starts at the etale fundamental group of the fibers, so that's just the geometric etale fundamental group of C. It maps to the etale fundamental group of the universal curve, and then that maps to pi1 of MG. So for those of you who have thought a little bit about fundamental groups of moduli spaces and mapping class groups and so on, this is like an etale version of the Berman exact sequence. And I just want to remark that this exactness on the left, the fact that the left map is injective, is not formal. So it's easy from the fact that MG is aspherical in the over the complex numbers to get a sequence like this. And then you're taking a profinite completion, but the issue is that profinite completion is not left exact. So it's not formal, and it would be formal if we knew pi1 of MG had some group theoretic properties, but we don't know those properties. So like this is actually something that requires a little geometric argument. Okay. So for the experts, the reason it's not formal is that we don't know that that pi1 of MG, so the mapping class group, is a good group. In the immortal words of Serre. All right, so now I'm going to make some obstructions to splitting this fundamental exact sequence, so to having pi1 sections. And those obstructions are going to be defined in terms of the lower central series of the fundamental group of C, our curve. So here I'm going to let Li be the lower central series of the etale fundamental group of C. So for example, quotienting by L1 is just the same as abelianizing. And remember, this is like a pretty concrete group. It's like generated by two G generators with one relation, just like you think. All right, so what we can do is take this Berman exact sequence. So here's the Berman exact sequence from above, and just quotient it by, well, smaller and smaller pieces of the lower central series. So at the very bottom, you get the quotient by L1. So I just told you that was, that quotient is the abelianization of pi1, so that's also known as the homology of your curve. So we have some obstruction of the etale fundamental group of MG by the homology of the universal curve, or fiber of the universal curve. Above that, we have an extension of pi1 of MG by the quotient of pi1 of a curve by the second piece of its lower central series. So that's some like two-step, like a metabelian group, and then so on. So above that, I haven't written it down. We have an extension of pi1 of MG by a three-step non-abelian group, and so on and so forth. Okay, so the first, this lowest line here, what I called star 1, it's very easy to get a cohomology class out of. Jordan, what's up?
Yeah, sorry, are we saying lower central series or derived series?
Lower central series.
Okay, so two-step nopotent, not two-step metabelian. I mean, it is two-step metabelian, but it's okay.
It's
sorry,
more than two-step metabelian. That's right.
Yeah,
it's two-step nopotent. Yeah. Great. Okay, so this bottom step, it's like pretty easy to get a cohomology class out of. So namely, we have an extension of a group by an abelian group, and such things are classified by, well, H2 of the right-hand thing with coefficients in the left-hand thing. And after massaging a little bit, you can see that that's going to be the same as giving a class in H2 of mg with coefficients in, well, the homology of the universal curve. And this is a fancy way of writing that. So this is a local system whose fiber is the homology of the fiber of CG. So the homology of C. Okay. So here's my claim. Like, I claim this actually satisfies the desiderata, like, from my strategy. So I claim this actually obstructs pi1 sections. So let me say write that out. So here, given the curve, so that's a map from spec K to mg, we can pull back O along the curve. And I claim that this pullback of this class O is 0 if and only if, well, not if my curve has a pi1 section, but if it has kind of an abelian pi1 section. So meaning you can take the usual pi1 sequence, you can just quotient by the derived subgroup of the geometric fundamental group. That gives you an extension of Galois by the homology of the curve. And I claim that, that this class vanishes if and only if this bottom sequence, so this extension of Galois by H1 of the curve, splits. Okay, and I'm not going to prove the claim, it's like almost tautological. The point is that, like, the definition of O was that it was the thing that obstructed the universal splitting of, like, that sequence. Okay, so this achieves step 1. So let me now describe a second obstruction class. And instead of working on mg, I'm going to work on the universal Picard. So this is the Picard variety of degree 1 line bundles on the universal curve over mg. So here, this is a thing whose fibers are pic 1 of C. So the fiber at a point C of mg is the moduli space of degree 1 line bundles on that curve. And then I'm going to define CG prime to be just the base change of the universal curve to that Picard variety. All right, so let me just remark, like, why am I doing this? Well, that Picard variety is a place where this lower sequence here splits canonically. And I'm not going to explain the details, but the basic point is that C maps to pic 1, and that map induces a isomorphism on abelianized fundamental groups. Okay, so we can just, like, replicate the whole story on P. So here I just told you that there's this canonical splitting of this abelianized fundamental exact sequence, or abelianized Berman sequence. And now there's a class O2 in the cohomology of P with coefficients in L1 mod L2. So don't worry about the details here. Let me just remind you, this is some associative gradient pieces of the lower central series of the fundamental group of the curve. And this class obstructs lifting this splitting here to a splitting like this. Okay, and in case you're interested, there's a sort of more explicit description of this L1 mod L2. So it's wedge 2 of the homology of your curve, modulo a one-dimensional subspace coming from the cut product. Okay. Now the claim is that this O2 is a similar obstruction. So it obstructs lifting a splitting of this abelianized exact sequence to a splitting of the quotient by the second piece of lower central series. All right, so that's a little fancy. What you should think about this is that it's sort of almost obstructing a splitting. So it's obstructing lifting a certain kind of splitting. So maybe it's worth remarking this only, like, sort of achieves step 1. So step 1 was to find something that obstructs the splitting. And the reason it only sort of achieves step 1 is that, like, given a splitting of the abelianized exact sequence, this O2 obstructs lifting it, but maybe there's some other splitting of the abelianized exact sequence that lifts. But in fact, this class O2 descends to a class on a certain quotient of this local system on MG, which simultaneously obstructs lifting all splittings. And it would take a whole nother talk to explain that, and so I'm not going to do it. But what you should think is that there's some other O2, which maybe I'll call O2 tilde, living on MG, which genuinely does obstruct this kind of splitting of the second piece of the lower central series. Okay, so let me just tell you like a little bit about these classes. So O1 and O2 are both Torsion cohomology classes. And in fact, O1 has been studied a lot. So by Morita, for example, over the complex numbers. So Morita showed that the analog of this class over the complex numbers, as long as G is at least 6, generates the group it lives in, so H2 of MG with coefficients in the homology of the universal curve. And that group has order 2G minus 2. And it's a little exercise to show that O itself has order dividing 2G minus 2. It follows from the existence of the canonical bundle, which is like a point on pick 2G minus 2. All right. So I've constructed 2 classes that I've claimed for you obstruct pi1 sections. Are there any questions about the classes before I show that they specialize in a lot of non-zero ways? Jordan, go ahead.
Yeah, do we know the order of O2? I mean, that was a class I thought a lot about, and I didn't realize there was a universal, in terms of the genus, a universal bound on its order.
Yeah, so O2 I think is probably 2 torsion, but I don't have a proof.
2 torsion?
Yeah, at least I can show the order is divisible by 2, but I can't show much more. And I'm pretty sure, so there's 2 questions, right? There's this O2 and O2 tilde. So O2 tilde I'm pretty sure is 2 torsion. Like I don't have a complete proof, but I think it is good evidence. O2 itself I don't have a strong feeling about, but that's still my guess.
But in any event, for any G, there's like just an answer. It is whatever it is, and that's a bound for any curve of that genus.
It's just a guess. It's only because I tried really hard to show that it was bigger than 2, and all I could do is show that it's 2 torsion.
Yeah. Okay.
Yeah. So I would be happy to be proved wrong. I think it's not so hard to see that there is a bound that only depends on G, so like meaning it's actually torsion over MG. And the point is like with any cohomological construction like this, like as long as it's sufficiently functorial, you can just like base change to a place where you have a rational point, like, and then co-restrict back down, right? So I think probably a universal bound is like the gonality of the generic curve of genus G. For a lot of these things. All right. So let's talk about degenerating Morita classes. So remember, like we've made these classes which obstruct pi1 sections. Now we want to like actually use them to do something. So for example, like it's not even, I mean, I told you that O1 is non-zero. It's not even obvious from what I've said that O2 is non-zero. So the way we're going to study them, remember, is we're going to try to find a divisor in the boundary of MG so that when we Geison our thing to that divisor, we get something non-zero. So let me tell you the schema for doing this. So unfortunately, the standard divisors in the boundary of MG won't always work, like the codimension 1 things. So we're going to have to make some new divisors. So let me remind you. So MG bar, that's the moduli space of stable curves of genus G. The boundary has a natural stratification, and the strata correspond to stable graphs, gamma of genus G. So what that means is graphs with some numbers labeling the vertices, and there's some combinatorial conditions on the graphs I won't get into, so that the genus of this labeled graph is G. And so what does that mean? It means you replace every vertex by a curve of every G, and every edge by a node, and then you compute the arithmetic genus of the resulting thing. So here in this example, I've drawn 3 vertices of genus 1 in a triangle, so that corresponds to this curve over the complex numbers, and this is genus 4. Right, so there's 1, 2, 3, and then there's that hole in the middle, which is 4. Okay, so given a stratum, well, what can you do? If you take the closure, it's a subvariety or substack of MG bar, and you can blow up MG bar at that substack, and then the exceptional divisor, which I'll call D gamma for a graph gamma, is a new divisor in the boundary of MG. Okay, so here's the main technical result in the talk. So first of all, let's talk about O1. So we're going to have to assume G is at least 3, although there are other graphs that work in genus 2 in effect. And then we're going to take the following graph. So it'll be a G-1 cycle where each vertex is labeled 1. And here there are G-1 vertices. So this corresponds to some stratum of codimension G-1 in MG. And the statement is that the Geison image of O1 in the exceptional divisor you get when you blow up this stratum is order divisible by G-1. Okay. So let me remark, like I just gave one example of graph, like we can produce a ton of examples of graphs for this, which this is true. We don't have like a great kind of pithy way of saying what those graphs are, but we have, if you give me a graph, I can pretty easily compute, meaning like 20 minutes, and tell you whether the Geison image of this class is going to be non-zero there. Okay, so for I equals 2, I'm going to have to assume G is even, and then I'm going to let gamma be the graph G over 2, G over 2. So it's just a line segment with each vertex labeled G over 2. That's why G has to be even, because G over 2 has to be an integer. And then the statement is that the Geison image of this O2 to the class, in fact, in some compactification of pick 1, but let me ignore that issue, is order divisible by 2. Great. So we've shown that these classes have non-zero specialization or non-zero Geison image at some point in the boundary of MG. All right. So are there any questions about that sort of main technical result? Or if not, I'm going to just start telling you about the sort of kind of what I think are cool corollaries. Okay, and I'm hopefully I'll have time to talk a little bit about the proof, but I want to talk about applications first. So the first corollary is like immediately we've just executed our strategy. So we get many in the sense of Chebotarev, trivial in the sense of not having any pi1 sections, examples for which the section conjecture is true over p-adic fields. And let me just remind you how those come from the theorem. Well, suppose you take one of these boundary strata. By Chebotarev, you can find an FQ point so that this Geison image here is non-zero at that FQ point, and then you just lift that FQ point into MG. So for those of you who have looked at Jakob Stix paper on providing examples of the section conjecture using the period index problem, it's the strategy is closely related. I don't think it's written in terms of Geison images, but there's some degeneration argument and you lift into the interior of MG. Okay, but this gives a lot of other corollaries too, which I think are cool. So first of all, the second example gives examples where the abelianized fundamental group, abelianized exact sequence splits. So you kind of have abelian pi1 sections, but no sections when you look at the second piece of the central series. So here, the second example gives, I think, sort of interesting, like, I don't mean to say that other examples are uninteresting, but sort of non-abelian examples of the section conjecture. Okay, so another corollary immediately is that the generic curve over the function field of MG has no pi1 sections. Well, why is that? Well, it's because if you in fact examine this Geison argument, you see that this class O1, for example, is non-zero when you restrict it to the generic point of MG. So that gives a very cheap proof of Haynes' theorem. And in fact, it gives a strengthening. So Haynes' result, I think, only works over sort of arithmetically interesting fields. So fields with infinite cyclotomic character, whose cyclotomic character is infinite image. But here, this result works over C. Okay, so it gives a bit more than that. So in order to say what it gives, let me make a conjecture. So as far as I know, this conjecture is original to my collaborators and I. So I'm going to take the function field of MG. Now I've defined all these like divisors in the boundary of MG. So these D gammas, and let me just remind you, we got those by taking a stratum in the boundary of MG and blowing it up. So if you have a divisor in a variety, that gives you a valuation on its function field. And this is going to be the completion at the valuation associated to this divisor. So this is some completion of the function field of MG. So then the conjecture is that the canonical curve over this field has no pi1 sections. And let me give this conjecture a name. Well, it's the same as the name of the talk. So it's the section conjecture at the boundary of MG. So why is that a good name for the conjecture? Well, it's because the universal curve over this field here is sort of the universal curve which has a certain type of degeneration, like the generic curve, which has a certain type of degeneration. And let me remark, I think this is like kind of a hard conjecture. Like, I don't think we even know that these curves have no rational points in general. So having no pi1 sections obviously implies you have no rational points, so that's a stronger result. Okay, and then a corollary of our result is that the conjecture is true for the gamma as in our main theorem. So for that cycle or for that segment with 2g/2s, and in fact for like many other curves that I haven't written down, or many other graphs that I haven't written down, but I can if you'd like. Okay, so in the last 5 minutes, I can talk a little bit about the proof and like where this is coming from, but maybe I should pause for questions first. So does anyone have any questions? And I remember I'm supposed to wait for 7 seconds when I ask questions, although that feels like an eternity. Oh, Jordan, go ahead.
Sorry, I do feel like I'm asking lots of questions, but this is very interesting. So in your
great.
conjecture, let me just understand formally, does this conjecture, I assume that in one direction, it being true for gamma, does that imply it's true for specializations of gamma or for things that specialize to gamma, or neither? I would think that one way would be.
I don't think it's so obvious. Let me think about it. Yeah. Oh, I see. I think it implies it's true for things that specialize to gamma.
Because you're getting as a corollary Haynes' original thing about the sort of.
Yeah. I think it's true for things that specialize to gamma. Yeah.
Okay, so it's harder as you go deeper into the strata.
That's right. So actually, let me remark though, I only gave a small collection of graphs, so we actually can do some things quite deep in the stratum. So we can do some, for example, zero-dimensional strata.
Okay.
In all large genera. So like the technique is actually it's pretty robust. You'll see in the argument like where there's some restrictions on what we can prove with the technique, but it at least is powerful enough to control some kind of very high flow dimension strata. All right, are there any other questions?
Yeah, I have a question about this conjecture. You're saying that we don't know if there's actually rational points.
Yeah, I mean, surely there aren't, but
if there were a rational point, wouldn't there be like a rational point over the boundary, and then you could argue that gives you a rational point?
Well, some of the boundary components do have rational points, Will, like the nodes.
But a rational point that's not a node. Like, aren't the nodes the only ones?
I think we probably know that. I would have to think about it.
Doesn't it follow from like the result about MGN that the only generic?
You'd have to think about it a little bit because there's these SNs happening, but yeah, I don't know.
Okay, yeah, that's
it seems very plausible. Yeah.
Very good point.
Yeah, but yeah, it seems very plausible. Yeah.
That's fair.
No, the rational point thing absolutely seems within reach. The pi1 section thing seems much harder to me.
Okay.
Yeah, I mean the pi1 section thing is really something about, like something inside of MG. So it feels, but I do think the rational point question is pretty approachable.
Pi1 of this thing maps to the pi1 of the residue field or something, right? So you could try to do something with that.
Yeah, that's right. Yeah, I mean that's more or less what I've been thinking about when I'm trying to do this. Cool. Yeah, I mean that map does have a pretty big kernel though. So. All right. So let me tell you a little bit about the proof of this theorem, and I'm just going to focus on this I=1 case. So understanding the abelianized pi1. So I only have 1 minute left. So let me just kind of show you the picture. So the idea is actually to do a complex analytic computation. So we're trying to show we have some class O in the cohomology of MG. We're trying to show its Geison image is non-zero. And what I'm going to do is, so remember the Geison map had something to do with like the circle bundle around the boundary divisor. So what I'm going to do is map a torus into MG so that kind of one of the loops in the torus, one of the longitudes, goes to a loop around the boundary divisor, so an inertial element, and the other one goes to a loop in the boundary. So here you should think of the map pictorially this way. And so maybe the red loops go to the boundary loops. And so pictorially, what does that mean? So it means the red loops go to multi-Dane twists. So or Dane multi-twists, I think they're called. So a loop in MG is a mapping class. So that's a diffeomorphism of a surface with itself up to isotropy. And so there's these mapping classes where you take a loop and just kind of twist it around 360 degrees. And the loop around a blow up of one of these boundary strata is just doing that in a bunch of different disjoint loops. So here's an example. So this is the G equals 4 case of the theorem with O1. So here, one of my mapping classes, so one of the sides of my tori is going to be the Dane twist along these 3 circles. And the other one is going to be this rotation, which kind of interchanges the components of the curve you would get by cutting along these surfaces. Okay, and it's not too hard to see that these things commute. So you get an honest map from a torus into MG, or at least a homotopy class of such maps. And now what do? Well, you just pull this computation back to the torus. And on the torus, it's something you can do easily. So in fact, for any given boundary stratum, running this computation is pretty easy. So the hard part is just finding the boundary strata that work. So I'm out of time, so let me just make one last remark. So this is a sort of like ridiculous remark, so you should turn your ears off now. So we're trying to find QP points where of MG where you have no pi1 sections, in particular where you have no sections. And under this arithmetic topology analog, QP is kind of like a surface. So for example, its tame Galois group looks like an extension of Z hat by Z hat. So it's maybe some kind of non-orientable surface of genus 1. So here what we did is we found actual surfaces in MG where our classes, our abstraction class is restricted to something non-zero. And then we used that computation to find QP, so these kind of arithmetic surfaces in MG where there are no pi1 sections. So I think that's kind of cool. And maybe just a remark, I mean, this topological question is interesting in itself. So it actually answers a question of Hillman, who asked if there were surface bundles over genus, let's say genus 1 surfaces with no sections. And so this produces examples for every genus. All right, so with that, I'll stop talking, and thank you so much for coming to this seminar.
Okay, let's thank the speaker the usual way. Thanks a lot, Daniel, for this great talk.
My pleasure.
Do people have questions?
Jordan, go ahead.
Hey, I have 2 questions.
Cool.
One, do you think, I mean, this game, as you set it up, is about the map from the universal curve to MG, or as one might say, the map from MG1 to MG?
Sure.
Can you play the same game with MGN+1 to MGN and get curves that have n points, but you can prove that those are all the points, sort of that's sort of like.
So I've just started thinking about that. Like I think the answer is probably yes, but it's early days, so I don't want to promise anything.
And then my other question would be this argument you make on O2. Let me understand. Would that allow you to generate examples where pick 1 actually has rational points, but the curve has no sections?
Yeah, so it's not totally formal from what we do, but if you actually compute in an example, it gives examples like that.
Oh, awesome. Okay.
Yeah, I think there may have been an example of that form in the literature, but I'm not 100% sure. So I think maybe if Jakob is still in the audience, maybe he knows. Okay, I don't know.
Yeah, I want to take one question.
Go ahead.
But very basic one, just basically about the introduction to your talk, about the Grothendieck conjecture itself, the section conjecture.
Yeah.
It is about finding splittings or talking about splittings when you act on the whole geometric fundamental group, which is a very big profinite group.
Yeah.
How about taking a small piece of that? And I mean, I know it's completely open. Like there's little.
Yeah. So I think we know that the pro-L section conjecture is false, if I remember correctly.
Oh, yeah, that's what I was going to ask. The part, yeah.
Yeah, I believe so. I think maybe you can already, I have to think about it a little bit, but maybe you can already see for abelian varieties that injectivity might, and so injectivity is true for abelian varieties if you don't parallel complete, but I think, for example, injectivity will be false with torsion points if you take a parallel completion. So I think probably if you take a curve which has a rational, like L torsion point sitting on the curve, probably that would give a counterexample. I'd have to think about it a little bit. Okay, so Jakob says that Pro-P is false due to Hoshi.
What about if you look at the pro-nilpotent one, say?
That's you mean like, but you're taking like a multiple completion?
Yeah, just take the product of all the pro-L completions over different L.
Yeah, I would have to think about it, but maybe Jakob knows. But my guess is I think this is I don't know what to think is maybe what I should say. I don't want to speculate.
Okay, cool. Okay, I think let's thank Daniel.
Jakob says pro-nilpotent is even falser. Right, sorry, go ahead, Mark.
Yeah, I want to thank you again for this great talk. Yeah, thanks a lot.
Thank you so much. Yeah, my pleasure. And I can stick around for a couple minutes in case anyone else has questions. Thank you, Jakob. I think it's nice to have the thing where people hang out after the seminar, so I'm happy to chill for a bit. And if you want to unmute yourself or show your video, that's fine too. Thank you, Jordan, and thank you guys for the invitation and for coming to the seminar. It was a real pleasure.
And Daniel, you're invited to come for real when that's allowed.
That would be great. Yeah, I would love that.
This was not like a one-time. You haven't shot your bolt. You still get to come and give a different talk.
That sounds good. All right, I'm going to stop recording.